Good. So again, welcome everyone. This is the second of the second Mipar webinar. This is going to be an interactive discussion, hopefully, of different topics about Mipar. Here I have just organized in folders here a little agenda or a planned agenda for the webinar. We'll start with a general overview, and I've got a couple of data sets that I think can quickly take us through maybe a common 2D processing workflow involving the image processor, batch, and processed image editor. We'll move on to some additional segmentation cases. You were in the same room. If that is the case, you should be able to just have a single mic for the entire room, so just have one person turn on their microphone, and then if each of you are connected over your own computers, then you can each have your audio playing, but just only one of you should have your mic active, if that's indeed what's going on. So image segmentation, we've got a couple cases, simple and complex. That will lead us then right into these three measurement cases, I hope. So these, I guess, in some sense would be a subsection of image segmentation, because I'm not going to, redo all the segmentation for each of these 3, 4, and 5. We'll just lead off from 2. And then I'm not sure if anyone's on who requested pattern mapping be covered. We had a couple of folks on Tuesday. Once I get to that, I'll ask and see if anybody wants to see pattern mapping covered, where we look at segmenting different texture or pattern from an image rather than intensity. Sometimes you don't have intensity differences between features, you have only texture differences. And then FFT filtering a little bit more. We might hit that in the segmentation if it's part of a recipe, but we had a request to cover that in detail. Although again, that may have been better suited for Tuesday, so we'll see if anyone wants to learn more about FFT filtering. It's pretty powerful. And then we'll finish up. I want to leave enough time at the end to cover some 3D analysis. I know we have a couple of folks on that have an interest in that. So we will do the best we can. Okay, any immediate questions before we get started? Just want to open that up. Very good. So let's get going. So this is Mipar. Many of you, I think, have used it. Hopefully all of you are at some point going to use it. We're on version beta 7 pre-release 5C here that I recommend you all get from the pre-release page. If you'd like to follow along, that would be the best version to work with. We should have the full beta 7 release, which is definitely Mipar's biggest leap forward, out by the middle of this month, so possibly next week. And that will come with full release notes for what makes a difference from beta 6, and that should be a pretty big document because there's been quite a few new additions since beta 6. So, overview. 5 applications. Image processor designed for single image analysis, recipe building. Probably the core technology of Mipar are its recipes. The image processor is where they're built and executed on individual images. Batch processor, take a recipe, apply it to a number of images, do your 3D reconstructing in here as well. Real time is really I call it a cousin of the batch processor. We hardly ever use it, but it's got great potential. Instead of being handed a folder of images to process that have already been acquired, it watches a folder, say on a data server. So as new images are saved off of a microscope, they immediately begin processing. So in theory, you could process one image while the microscope is acquiring the next image. Again, big potential. We haven't used it too much though. Processed image editor, review your batch application of a recipe on 2D images. See how the segmentation did, clean up mistakes, make measurements from all images at once, kind of your 2D review environment, and then finally your 3D review and much more environment where you'll take image stacks and reconstructions made in the batch processor and do additional segmenting if necessary, cleaning up, visualizing, measuring, movie making, that kind of thing. So the more details of this overview, I'll start by opening up the image processor and taking a look at an example image I've got ready. And we'll load in a recipe and take a look at what's going on. I think most of you are familiar with the layout here of the image processor. You have all of your different tools available on top, your image processing library, shortcut bar for quick access to commonly used functions, interactive image analysis and measuring tools, your pixel to micron conversion to calibrate your magnification, and yes, we are working on adding support for other units beyond microns. For now, just convert everything down to microns, although most of us, I think, work in microns pretty typically anyway. Image properties, a help box that shows information about the different tools that you're using, either as you pick them from the menu or as you show an image from the recipe, you'll get a description of what that tool did, and all the other elements in here, if you hover over them, they'll have tooltips that explain a little bit about what they do. And let's open an image to see the rest of it. So we've got, let me go ahead and add a shortcut here. The image I have prepared is this SEM micrograph of some composite matrix and reinforcement particles. I don't know much more than that. And we see we've got link, zoom, and pan viewers. So as you zoom in and pan around in either viewer, you have a synchronized setup where this at first is your original image and will stay as your original unless you set a recipe item as your reference. But this is just kind of a before and after view that always lets you see where you've been and where you are. So we can load in a recipe that we've made to segment the matrix and the precipitates from each other. And there we have it. So that is the last step of the recipe that's shown. That's what the matrix selected. Very important to note that in Mipar, the convention is that what's black in your binary view is what is selected. So really what we've done is we've found the grains at this point. Just double click on a step to show its result, and then we've inverted it for the last step to select everything else. These are labeled with stars and capital letters indicating that they are layers that have been set. We'll talk about layers, I'm sure, throughout. There are ways of setting steps as important that then give you certain advantages in other things that you do. So what have we done here? We started with a global threshold to try to select, well, in this case, technically, yes, we're selecting the matrix, but since we can always invert the image to get the particles, we're trying to best segment the two phases here. You have your controls down here, show an image or show a step, edit a step, remove a step, disable from here down. That we did encounter a bit of a bug with that yesterday, so I'll be careful when I show that. What it lets you do is, okay, so if you were to make a change at any point in the recipe, remove, insert, edit a parameter, let's say we take our global threshold, and here's the image we're working on, we're trying to convert it into the best segmentation, move your slider, adjust what you do. Let's say you fiddle with the parameter, you hit accept, the rest of the recipe gets automatically reperformed so that edit now propagates down all the way through the recipe. So no need to delete back your work. You have a fully non-destructive processing sequence. What disable here or down would do is, if you went, say, down here, and you wanted to fiddle with steps up in this part of the recipe, but you didn't want to wait for the watershed and everything under it to happen, since that can be time-consuming, you can hit disable here down, and that will turn off these steps from being auto-updated. So now if I went and I edited this, those last steps at the end still get quickly checked for errors, but they don't actually get performed, which means that they're not up to date. So you shouldn't treat this final image now as the proper endpoint because it hasn't been updated, but it at least lets you fiddle up here without waiting for some steps to perform. So to see it updated now, click at the bottom of your disabled steps, and this button now says enable here up. So if you click that, then the steps that were disabled get redone, and now this is an updated view considering the whole recipe. Here we have a trash can, clear out the entire recipe and start over. That used to only be possible by opening a new image, but now you can do it with a single button. When a recipe is loaded, if you open an image or choose to open an image, you now are faced with a drop-down, so you can open an image and clear out the recipe, or you could say, if you're wanting to see how this recipe did on something else, choose to open and reload a recipe. It's telling us we haven't saved this recipe since we last changed it. So we can choose to do that now. I'm just going to give it a new name. Now it'll save that recipe. It'll ask what's the image that you want to open next. Let's say this is a different image. It'll open that image and then confront us with some sort of issue. Well, we're about a few minutes in, so that was bound to happen at some point. Let's try it again. We'll make sure that gets corrected, of course, before the next release. If you've loaded in a recipe and you're seeing how it did, okay, there looks to be some sort of issue there with the auto reload function, but we'll get that taken care of. That's why this is a pre-release, I suppose. Okay, so we have let me jump out of this and get started fresh. Make sure we don't run into anything else. So let me walk through the steps that were performed here quickly, and then we'll move on to the two other applications and then dive more into segmentation. So let's actually show this function working now. Pick a new image, and then that recipe gets reloaded in. There just seems to be some kind of issue with saving a changed recipe and having that save get reapplied, but we'll get that taken care of. If you just save the recipe, once you're done with it, then when you choose to open a new image, you can reload the recipe on another image if you want. Okay, so we have a global threshold step. We then did some noise rejection and some more noise rejection. Let me mention now also that we've got different viewing modes. So this is just a black and white, a binary view of the current segmentation. But we can look at an overlay of the segmentation on the original with different opacities. We can look at an outline on the reference. And finally, a unique colorization of the separate features. Now this is remember our binary view, this is the matrix that's selected, so it seems to basically be all one feature. If we went down to this point in the recipe, okay, here we've rejected some very small black features. We've gone from that to that. And now in this step we've inverted to start to select only the precipitates, and this is how the labels looks for that. If you just want to see all of your features overlaid as some single color instead of a map, just switch to single color mode and pick your color. Now you've got a color overlay. So what we've done here is now say, well, we see a number of these particles are connected. If we go back to a color map view, this cluster here needs to be separated. So we have a tool called a watershed tool to do that. The trouble is that it can do some strange things at certain strength settings to very small precipitates. So what we chose to do is put this image away in memory in this restore image slot. That was done, memory set restore. And then we kept very small features to preserve them, to add them back later after we ran the watershed on the entire image. We put this in a different memory slot so that it can be combined with another image later at the end. And then we brought back this state with all of the features. And then we ran a watershed to separate everything. And if I can find a little example of, yeah, this little guy right here. You run a watershed and it gets split unnecessarily, but that's why we put it away back here in the companion, preserved, so that we can take the full image, do our particle separation that works real well for bigger features like this, and then add back in those little features so that they're intact, if we want them to be. Honestly, we could probably add another noise rejection in here that would get rid of small features, since I don't think that's a particle right there. But why don't we do that to demo something? So let's add a reject feature step here and see how big this is. Click your measurement tool, double click it. It's 12 pixels. Let's just get rid of black features that are less than or equal to 20 pixels in area. We have all these other measurements to choose from, of course. Perform that. Those go away. Now this is probably what I would want to call my grains rather than this step up here. So let's just remove this as a layer and call this our grains. Set that as a layer. You can set layers either by right-clicking on a step or by going into the layers view, which is where you can see all layers overlaid together. Here we just have one, the matrix. I can take, and you'll see what's being selected down here when you go to these different steps. So this is my grains step in the recipe. So I'm going to add this as a layer, and I'm going to call it grains. But again, that also could have been achieved a little more quickly, and this is something that's new to this pre-release. You can just directly set layer steps from the recipe, and then they'll show up in the layers view when you open it up. So there we have our segmentation at the end. You got the matrix in blue and the greens, or the grains in green. Take the image if you like. You can look at this as an outline or overlay. Outline isn't very good for two phases that are interfaced with each other. This would be better for if you had, say, one layer where the big particles were found and another layer where you had smaller particles. That's when outline can be helpful. Right now, the blue and the green is directly overlapped, so it's not very helpful. I like overlay view for this kind of a setup. So that's a quick recipe. We've got other measurements, of all kinds of measurements that are possible, but I'll save those for when we go into that section of the webinar. I don't have multiple images like this, so to show quickly the batch and the processed image editor, I'm just going to open up a different image here, one of these gamma prime gamma images, and we'll load in the recipe that we made to separate out the large and small particles from each other. So at the very end, this is all precipitates found together. But what we've said as layers are the tertiary, just the smaller ones, and the secondary, just the bigger ones. So here is where outline view can be handy to see them together. So you have this recipe. If you had a set of images, like we do in this case, whoops, we've got a few images from this microstructure, and we want to process all of them this way, then we can either launch the batch processor fresh and load in our recipe, or if we launch it directly from the image processor, then the last saved recipe gets automatically brought in for us. Let's choose where we want to save the images. I'm going to put it right in here. Instead of processed, I'm going to suffix them with segmented. And the images to work on will be these 4 here, 5. None of these other options are necessary here. Mag calibration, if the recipe has a scale factor saved into it, then that would be loaded in. If you had a cal file saved separately, you could load that in here, or you could measure the calibration or just type it in if you know it. This allows you to make measurements in physical units of microns instead of pixels. But if you're only, let's say, measuring area fraction, then you don't need to worry about the pixel calibration, and we're not going to in this case. The rest of these are mostly used for 3D reconstruction. So the batch processor has finished. We can now just review the processed images, which will open everything up and package it all together in the processed image editor. So what's actually been output file-wise, if we go back to our, this was our save directory here, and we get a folder that has the same name as the suffix that we used, segmented. In this folder, we've got binary images for each layer for each image. So we've got a secondary and a tertiary for each image that we processed. And the lines there are a Windows display artifact. I'm not sure why that happens. So the processed image editor has taken all this and loaded it in for us, and we've got now all of our tertiaries, and we can switch to the secondary layer, or we can even view in layers mode and see everything together for all of the images. So usually the point of this is to make measurements. If the segmentation isn't perfect or accurate enough for a given image, you've got manual editing tools down here to clean up the different layers, the different images. In severe cases, you might need to reopen one of the images, which will, if you click this here, this will open that reference image here in the image processor. I think that issue is connected to the one that we noted yesterday, or sorry, a moment ago with the auto reloading not functioning. So we'll get that fixed. But there the image has been opened in the image processor, and you could reload that recipe. And let's say this was a really poor image that came out, you would be able to, let's say you needed to use, for whatever reason, a different threshold on this image. So you would adjust that, let the recipe update, and maybe it was the secondary layer that was really poor in the processed image editor. So we can go to that secondary layer, save the black and white image here, overwrite what the batch processor spat out. So this was I-49. Let's say we're going to overwrite that image's secondary segmentation. And now when we go back to the image processor, if we just click refresh, now that new image is there because it's reading it off of the hard drive as it displays it. So that's a way to somewhat quickly run a different recipe on a certain image if it needs it. Hopefully the segmentations are not ever too inaccurate such that manual editing can't fix things. So if you needed to remove a feature that was a false positive, let me just switch to outline view so I'm sure of what layer I'm in. The secondary here, let's say you wanted to remove a couple of these features, then you can use your select tool, and you can click on the features you want to remove, double click the last one, or click and hit enter, and then we'll choose to erase those features. And then if there were ones we wanted to add, we could freehand those in. Like that. We do have a region grow tool that is somewhat of a magic wand. It can take a little bit of fiddling with the tolerance to get it to work right, but let's see how it works. So if I do region tool and I double click on this feature and hit fill, so it needs to be a little bit broader. So let me up the tolerance to 40. Try 60. 80, I suppose. Yeah, so that could be a way to quickly fill in missing features without having to freehand everything. You can do it on a couple of things. And that's way too big of a tolerance for those two, so undo that. Let's drop it down to 30. Now, any edits that you've made, since you have unsaved edits, meaning that the ones that you've made have not been burned into the image that's on the hard drive, this one, you're not allowed to advance the slider. You can type in a new image if you wanted to go to it, or you can double click on a new image if you wanted to go to it, but it's going to warn you that there are changes that you've made that have not been saved. So if you do go to that image, you'll have to choose to discard those changes. But if you just click save, then it'll take the edits and make them permanent in this particular image, or you can save as and give the edited image a new name. Say we'd call this one secondary edited. And now the edits are saved, but you've got now the manually edited version here in the list, so you can keep the auto and the semi-auto segmentations separated. And now your slider is back here. Okay, so we've gone in here, we've reviewed, we've made some changes. We can look at layers, of course. We can save images for reports. And finally, you can make all of your global measurements here if you wanted to measure, say, the total area of the secondary and the area fraction of the secondary particles. These measurements are generated off of the current layer, so, you know, the secondary is the current layer even though you're seeing both of them. The secondary is the active layer. So if we hit generate now, we would get, we call these global, we would get those measurements made for every segmented image. Come over here and take a look at this in Excel. There we have it. And we could do the same thing for the tertiaries. If we wanted feature measurements, so a metric per feature, say the size of each particle, feature measurements, pick off the ones you want, call this local. Let me do area per particle and eccentricity per particle. Now we would get, you'll see what we'll get. We'll get one big spreadsheet that has every feature for every image in it here in local, got the first image here and all of its particles with area, eccentricity, and diameter. And then we go down and here's the next image with all of its particles, so on and so forth. But sometimes, in addition to histograms of feature measurements per image, you also just want the average eccentricity in that image, or the average size of the particles in each image. So we also export a means version of the file that has the averages of the measurements that you made per image here. And we've had requests for including the min, the max, and even the standard deviation of all of the measurements made in that image. So we'll add that feature, and you'll have, we'll either put it all in one spreadsheet, so you've got a mean section, maybe even a tab, a mean section, a standard deviation, a min, and a max, or we might have a local means, a local min, a local, or a local max, you know, different text files for the different stats of the distributions. We'll probably put it in one file because I think that would be more helpful, but we'll try to work that feature into the next release, or the full release. So that's probably a decent overview there. 40 minutes was a little longer than I had planned for that, but that's what a typical 2D workflow can look like in Mipar. Are there any questions or comments at this point before we dive into some other segmentation problems? Okay, very good. So let's do that. Let's head back to the image processor. What other images did I have for us to work with? That was what we probably looked at. I'd call the first image there maybe a medium level difficulty of segmentation. Something very simple, might only involve 4 or 5 steps or 1 or 2 steps. And I did say we'd look at simple and complex problems. Why don't we, well, we got a couple of submissions from some very generous folks. Abhishek, if I'm pronouncing that correctly, and Austin submitted their problems that they're working on. Thank you very much for that. Why don't I start with these laps here. This is one slice from a serial section data set. And he was kind enough to also provide the rest of the images, not the a subset of the images. So we could look at that subset as part of the 3D tutorial, or the 3D section. But I can just use this image to demo maybe sort of a simpler to moderate difficulty segmentation problem. And then Austin, thanks very much for submitting your image here, where I worked with a cropped version of this image, or can work with a cropped version of this image, and look at how we can segment the 3 phases in here. We've got these colonies of alpha and gamma, and then we've got these gamma globules, and then a beta matrix. And this is much more of an involved problem, but we have the tools to do it. So what I'd like to do is probably see if we can build this one up live, if everyone is interested in that, because I think that would show a lot of helpful thought processes and tools that go into building a recipe for this. Of course, we're always willing to build a recipe for you and send it over. We've had hundreds of folks send us their images and get recipes back, sometimes inside of 10 minutes. So that service is always available to you, and we think that's what makes Mipar very, very special. So let's start with the last problem here. I will clear this one out. Now here's a case where if you're just after this one image, you're obviously going to crop this thing down. And that's fine if you're always going to be applying this recipe to this size image. with the area of interest in this area of the image. But if you can avoid it, I tend to prefer to pre-crop your images rather than have a crop step be part of a recipe, because if you take this recipe and you run it on some other random image that's 2048 by whatever, then obviously the crop square that you've drawn for this image won't mean anything sensible for the next. So that's why I like to, in this case, if I was just trying to segment this one image, I would probably crop the area to something like that. And then I would go and I would save this image here as 37 cropped. And then I would reopen it fresh and start building my recipe now on this image. So let's take a look. First thing I note is this sharp change in brightness. That would definitely pose a problem if you wanted to global threshold this thing. Let's first take a quick look. It looks like we might have a little bit of noise in here in the image. That's okay. We can probably work with it present. We could probably segment directly off of that, but we can certainly put a little free window size median filter on this thing and clean that noise up a little bit. So let's start from the raw data and see how it goes. So if you wanted a global threshold, which is your simplest thresholding approach, first of all, the histogram tells you you're in for a bit of a struggle because there's not a clear separation of pixel intensities that would separate the different phases. As you move up, we're going to see exactly what you would expect. But that's not going to work. We could try a background flattening step first under pre-processing, which has all of your grayscale manipulation steps. And what this is doing is it's blurring the image and then subtracting that blur from the original to give you this background flattened effect. But because this is such a sharp change in brightness, I'm not sure that that's going to be very helpful for a global threshold either. So we could try that background flattening, and then we'll see how the global performs. It's not quite as bad, but you're really not going to be able to use this to separate the entire image. Of course, what you'd like to do is, and maybe this gradient does go away later on in the stack. Maybe this is a milling artifact. Maybe you have to throw this slice away altogether. There are plenty of things you could do. I just want to see if we can segment this image, knowing nothing else about the data collection or the rest of the data set. So what I'd probably go with is an adaptive threshold. That looks at, because we know still as humans that even though this phase is, this feature here is surrounded by overall brighter material or brighter image content than the same phase down here, we still know this is a phase because it's brighter or it's darker than what's surrounding it, which is exactly what the adaptive threshold looks for. It analyzes each pixel relative to what's right around it instead of relative to some arbitrary 150 cutoff that you set with the global. So if I go into adaptive here, 30 is our default window size because that strangely tends to work well for most images, but it really depends on the scale of your features in pixels. So if I take my distance tool here, I can get a feel for what my feature scale is. 30 pixels looks like that, and that would kind of start to nicely span a lot of these features. And what you're doing is here, you're looking at every pixel, say this one here, and you're considering a window around it. So if you use 30, your window side length is going to look something like this, centered about this pixel. So you're going to take the average of all the pixels that fall in that window, and let's say that's 100, and this pixel value is 90. If I set a percentage of 95, then I'm saying that in order for this pixel to get selected as white, it needs to be more than 95%. Its value needs to be more than 95% of the average that's around it. Or you can work in departure mode and say that that pixel has to be more than 5 intensity units away from its local mean to be selected as white. So if the mean was 100, that pixel value would have to at least be 105 or bigger for it to get chosen as white. Otherwise, it's black. So as you increase this value here, the pixels need to be a greater and greater distance away from their local mean to be made white, which is why you see fewer and fewer white pixels. So I, for whatever, probably more of a preference, like to be in percentage mode, so that's the default starting mode. And now the task is to start playing with your parameters here to get the best segmentation. We do have an optimization function that lets you have Mipar auto-determine the best parameter values. We can get into that. But why don't we demo that here on this particular image once we come up with what we think the best settings are. So we move this around, get a feel for what's going on. We can try increasing the window size, see if that helps. Okay, so it's noisy, but we're starting to make out some structure. And we have some noise cleanup steps that are more intelligent than just a brute force erosion and redilation, or a closing or opening. And those are our classic steps here. If we took a classic erosion, what this will do is it will grow white pixels, otherwise known as erase black pixels, based on what's around those black pixels. So we notice over here we've got kind of a lower density of black pixels than in here. So Mipar should be able to tell you that, well, that's probably then your white region, and this is probably your black region. So there are a couple of parameters in here. Depth is set to 10 by default. That's really just an iteration count. That's the number of times this function is going to be looped through the image. Coefficient is really a strength setting, and it sets a threshold for what gets erased, what gets made white in this case. So each pixel has 8 nearest neighbors, 4 on the faces, 4 on the corners. If you say a coefficient of 5, you're saying that of those 8, at least 5 need to be white in order for this pixel to get made white. If you say 6, then 6 of them have to be. If you say 7, 7 of them have to be. So that's going to reduce the number of pixels that get switched if you go from 5 to 6 to 7. So 5 is going to be a stronger behavior than 6. So if I put in 6, that's what I'm left with. If I put in 5, that's what I'm left with. And then what I would do is do the same thing, but for the other color. So we'll do classic dilation here, and I'll use 5 again. And now we're left with a little bit of artifacts, a few artifacts that were a little too coarse to get removed from that cleanup step. Here's one, and here's one, probably. And we see why those didn't get removed. Perhaps if we had switched the order, if instead of going erosion and dilation, let me try that. Let me erase dilation, go up here, put in dilation below this step. That's the issue there, is you're probably going to have to go with a 6 and then a 5, and then you end up with that. So I think first order is better, and we can get rid of those other remaining artifacts with something else. So we'll do an erosion first, and then a dilation. And now we can get rid
John.
of... Yes.
Hey, did I, sorry, this is Austin and with Alcoa. Did I miss the TNM example?
No, you didn't actually. We started
great.
this one first, Austin, and we're just going to get to yours after this one, so perfect timing.
Sure, great. Thank you.
Yep. Okay, so these couple of features here, we can go after the white ones first. How big is this? 16 pixels, so 20 is probably good. You want to get rid of this feature, maybe up your threshold, or click on it to choose it. To measure it, I should say. That one's 42, so we just missed it. And now we'll do the same thing, clean up reject features on the black ones. And why not pick the same value? And there we have our segmentation. Not too bad, all things considered. If you want to do some smoothing, so the roughness here is related to the noisy nature of the image. Yes, sir.
Yeah, John, this is Abhishek here. So I have a problem with the segmentation. If you look at the top right corner of the segmented image, you will see that the features are really fine there, and the steps have actually clubbed 2 or 3 of the lamellae as a single feature.
Ah, I see. Yep. Okay. Good observation.
So can something be done for that?
Yeah. That's very good observation. So this is actually quite a good example here where you've got a gradient in your size scale. So one window size may not work well for all, or you might need to go to a finer window size and then work with the noise that introduces into the bigger features. So let's take a look. Let's go back to our adaptive threshold step while still looking at this final state of the recipe. So we're just going to make some changes here and then see how they pass through. From the adaptive threshold, those lamellae are not too badly captured, so it must just then be in the remaining noise processes that the features get eliminated. So the erosion kept them intact. The dilation is where we went wrong, because we started to split those now up into little pieces that then got erased in our reject feature step, and yeah, there we end up with the issue. So, of course, sometimes, this might tell you that if there's any way you can adjust your imaging conditions for a clearer or higher contrast image, then you might have to do that if image processing can't help you. But of course, we always like to find a processing solution because sometimes we're at the mercy of our instruments. So what I'd probably first do is maybe try changing this from a 5 to a 6. We may not need as severe of a noise rejection since we've got other ways of getting rid of it. So let's, instead of 5, which performed like this, let's do 6. And now more of those features might be intact here. Still going to pose a little bit of a problem though, I think, because those artifacts, those are going to look like artifacts, just like these will. Now we do have some conditional other traits that we can add to the reject features and say only get rid of small features if they're by themselves rather than clustered around other ones. So that could be a way to avoid getting rid of these, but why don't we, like I said before, why don't we try to play with this adaptive threshold a little bit. Maybe even do some contrast enhancement prior to the adaptive threshold. So let's first take this window size down to 30 and take this down to 100. That's probably too noisy. Let's try 102 and see what we're left with. So now we're faced with the issue of the lamellae getting a bit split up. Let's go to the very top, and before anything happens, let's try either a mean or a Wiener filter. A median or a Wiener can be helpful noise cleanup. Let's try a Wiener of 3. Let's go and set the Wiener as the reference. Let's edit the adaptive threshold now. We might not need as much of a strength. Hundreds probably too. Sometimes with low contrast images like this, you can get very sensitive around the critical percentage. 1 or 2 values can make a big difference. So there's 30 and 100. There's our noise cleaned up. There's our noise cleaned up. Maybe we don't use as big of a value as 45 now. Although up here in the corner, I'm honestly not too sure what to even call the right answer. We can say that we can avoid getting rid of edge features, or we might just have to call that corner. We might just have to sacrifice that corner. So there is a segmentation that might keep those lamellae more intact. Does that look a little bit better? Aside from the top corner.
Yeah, John, I think we have to live with a bad image anyway, so that's fine, I think.
Okay. You could add some smoothing on here, so the roughness on the features is just, I mean, in fact, you've got a digital microstructure made up of square pixels, so turning a grayscale continuum into a binary is always going to have some kind of roughness to it. Noisier images, the roughness is even worse. We've got a smoothing operation that can get rid of some of that. The strength is determined by the window size. Of course, as you go to higher and higher windows now, in addition to smoothing, you also grow features together and dilate them a little bit. The growth and the dilating can be controlled with this threshold, but I probably wouldn't really want to go more than 3 for this microstructure, maybe 5. And then we might want to back off this, or go up on this threshold a little bit. Now we just kind of have a rounding out of the edges with no real dilation or erosion. Now we see that a little artifact like this got disconnected, which means that we can go add another reject feature step of the same setting to get rid of anything that was broken free from the smoothing. So that is one segmentation that you could come up with for this type of microstructure. Hopefully that's the segmentation. I talked about more objective parameter selection. So up here in this critical adaptive threshold step, we came up with 30 and 101. That's, in this case, based on experience. And the question of segmentation accuracy involves a whole, sometimes messy discussion of what's the microscope doing to the, how is the microscope interpreting the microstructure, and what other sample preparation issues could have added to. You have to, I guess, always remember that the image of the microstructure is really just that. It's the image. And the best that you can do in this case is have Mipar objectively say what's the best binary representation of that image. What that image says about the microstructure is a whole separate question that sometimes only a human being can answer. In the absence of forward models that can predict how a microscope will interpret a microstructure, we're really just left with our own experience and our own knowledge base. So that's what Mipar is able to do, is measure a degree of similarity between the segmentation and the original image or some reference image. So to see what it comes up with, we do have an optimization tutorial, I believe, up on the website. So feel free to hit that up if you'd like to look at this a little bit more. But steps that are optimizable, the button lights up. So let's say optimize that step, and we get this little dialog. We're going to use the prior image as the comparison, which in this case is that Wiener filtered image. We're going to work with the whole image, not just the subregion, and we're going to use mutual information as the number, as the image similarity, or the critical metric. So this is a metric of how well the black and white describes the original. Interclass variance is another way of measuring that. Sometimes you come up with different responses and one is clearly better than the other. Feel free to read up on these. There's lots of documentation on Google about what each of them does. Or contact me. I'm happy to talk about them further. And yes, we are working on a user manual for Mipar, thankfully, that will include some more elaboration on these things. I don't know if this is, these things haven't been tooltipped yet, but our intent by Beta 7 is to have everything that you hover over have some more information. So there will be tooltips on each of these that will explain more of what they do. Number of features was something we were playing with, trying to choose the parameters that led to the most stable number of features on a curve of segmentation value versus number of features. What we'd also like to do is add all of the global measurements as metrics for interrogation to be able to run sensitivity analyses to say, as you vary the threshold value, how does the area fraction respond? And then you might want to choose the threshold value or the parameter that causes or that the area fraction is least sensitive to in that area. But that is not in here at the moment. So what we're going to do now is just take a look at how the mutual information varies against some parameters that are varied. So we've got two parameters here, window size and threshold value. For this example, we'll say that we're happy with our window size since that seemed to have less of an effect on the segmentation as our threshold selection did. So We're going to fix the window size at 30, and we're going to let the threshold vary from 90 to 115, let's say, in steps of 1. Now Mipar is going to go and it's going to try out the segmentation at each of those values and come back and say that at 101, we've maximized our mutual information with respect to our threshold value. And I promise I didn't look at this ahead of time. We just happened to pick 101 as the manual selection, so that should give us some confidence in our experience. But this now at least gives you a defendable way to say, well, so someone asks you, why did you pick 101 instead of 100? Well, I don't know if 101 is right. I don't think anybody does, but at least you've got an objective thing to fall back on here to defend your selection. Now with that step optimized, you've got 2 asterisks in front of it that indicate it's optimized. So if you hit edit on that step now, instead of the usual adaptive thresholds interface, you get the optimization interface, so you can rerun that thing that we just did, change any of these settings, or change your parameter space. If you went and optimized both parameters, so let's also let window size vary from 5 to 50 in steps of 5, let's say. Go to 80, why not? Now you're going to run through bunches of parameter combinations, all the thresholds at 5, 10, 15, so on and so forth. And you're getting mutual informations for all of these now. Let me redo this with a little bit smaller range, just so we're not waiting around too long. Now, often what I find is when trying to auto-determine both parameters at once against the original image, it tends to always say that the highest window size in your range, one of those thresholds in there, has the best selection. So we see that's exactly what happened. As the window size grew, the accuracy continued to climb and climb. And I think this would always be the case regardless of what window size you chose. And I'm not sure if that's a better, I don't think that's a better selection than what we had with the finer window size. Remember, we're using the whole image, so we've got coarse and fine features. The trick that I found that tends to give pretty reasonable results, and I don't really have a scientific explanation for why, is to compare the segmentation against a high-pass filtered version of the original instead of the original. So to do that, you can just take your in this case, our Wiener filter. I'm going to put this in the memory slot of set restore image number 1. And now I'm going to make a high-pass filtered version of this image, which means go into FFT filter, say I want to do an ideal high-pass filter with a sigma of 20, generate that, maybe a little bit less. This is blanking out low frequencies in the image, so it's making the edges of the features more significant in the image. So I think that what this is doing is it's when you're comparing the segmentation to this instead of the original, you're comparing it to more feature information and less background information by doing a pre-high pass filter for your comparison. I'm going to say accept that, set the FFT filter as this memory slot, and then let's bring back the Wiener filter to actually run our threshold on. So we're going to threshold on the Wiener, but we're going to compare the segmentation to the high-pass filter, this one. And we're going to do that just by editing the optimization, and instead of comparison of prior, we're going to use a comparison of restore image 2, since that's our FFT filter. But again, we're executing the function, the adaptive threshold, on the Wiener filter. We're comparing, though, to the FFT filter. And now let's plunk in our range and see if we can come back with a peak in that surface that's within the, not at the edge of the parameter space that we explored, which is what we would ideally like to see. I think the the best parameter combination has to be somewhere in here. So there we did. We came back with 25 and 100. And I think manually we had come up with, 30 and 101. So not too bad. Of course, let's see what the end product looks like. So I think that in this case, we might want to take Mipar's suggestion of 25 for the window size. Well, let's unoptimize this step and just bump up the percentage to 101, since maybe even 100.5. We'll call that a good compromise, because at the end, it's a better segmentation. So it's clear that there is no magic button that's going to come up with the absolute end-all be-all segmentation, but I think we do have the tools to help you get much more precise than other packages can, and there's some objective measuring going on. And then you, again, have a defendable reason for choosing your parameters. I'm usually comfortable choosing the window size based on the scale of the features and then having Mipar come up with the best threshold value. So I'm going to go back and say 30 and 101 is what we're going to go with. Okay, and now we've taken, here are our precipitates. If we wanted to add a layer to find the matrix, then we would just invert our segmentation, and now this is the matrix, and then we could set up those layers to do that and run this recipe, say, on all slices of the reconstruction, and come up with a 3D reconstruction of both the matrix and the laths and the features. So there, we built one up fresh for this type of microstructure. If there are no questions at this point, and please speak up if there are, we'll move on to Austin's image with the three-phase microstructure. Okay.
Hey, that sounds good. Can you just give me 1 second while I go grab Thomas?
Yeah, no problem.
It'll just be like a few seconds. 1 sec.
No worries. I'll get the image.
All right. Hey.
Hey.
So Thomas is gonna join us in a second. It's okay. You can start with that.
No worries. Great. Okay, so here's the image that Austin supplied. Again, thanks very much. What I did, or what I would do, is I'm just going to pick this area down here.
Yep.
And let's save this image as cropped. And we'll reopen it with a clean recipe. Okay.
Hey, John. Also after this, I have a question, but I can wait till the end of the seminar.
Okay.
That's unrelated to this microstructure.
Okay. No problem. So, I started off, my approach was, when just thinking through this here, let's try the global threshold to find the darker phase. So what we've got again is we have, I guess, an alpha-gamma lamellar structure here within the colonies, and then gamma globules, and then the remaining beta bright matrix. So we might be able to separate out the lamellae somewhat, but if you're after a lamella spacing, you're most likely going to need a higher magnification image inside one or two of these colonies. So what I want to first do is see if we can just segment colony from gamma from beta, and then go from there if we need to. If that sounds okay.
Yeah, I realized it was sort of a tall order after I sent it,
Sure.
so it's okay. Yeah.
It's possible. We can see what we can do, but I think I'll try to get that three-phase done so we can all see the steps and the thought process, and then maybe Austin, you and I offline in another session can look at really digging into this image to see if we can get some work done.
Or you can just talk about near the end, not if it were bigger, how you would do it.
Mm-hmm. Okay.
It's not always like this. This is a specific example. Typically, it's a little bit bigger.
Okay. That sounds good. So even though there's not much of a gradient in here, because I'm going to start with a global threshold to go after the darker ones, I just, out of habit, put in a background flattening with the slider somewhere around 3/4 position, and that helps flatten out any little gradient that might be in there. And then let's go into the global threshold here, and let's start taking a look around. So this hump tells you that probably your selection is going to be in that area. And I think if you went with something around 76, that's going to be reasonable for the gamma. Now we can say that really, really tiny dark features we might exclude from the gamma population, or you can keep them in if you like. I'm going to get rid of very tiny features, take a look at the outline. Here's our gamma selection so far.
That's great.
And now these little ones up here, these are just some pixels that happen to be a little lighter in the gamma. So let's go in and do a reject, but on the white with 20, close those up. We're seeing now that we're going to have to make some choice probably about this this gradient that moves away from these features, but we'll get there. And now let's go ahead and put this away in memory, because we're going to combine it with something else to get our three-phase segmentation. So this one I'm going to put in the companion slot. And then we're going to go, we want to get back our flattened background image, so we'd want to set this up as the first restore point, so that we can call that right here. And now let's try the threshold on the brighter phase. We'll do a global threshold, and we'll go up here to pick the brighter phase. Now as I move down here, kind of my things that I'm looking for, I don't want to include a lot of mass inside the colonies, but I do want to get even little specks like this up here. There's also a gradient away from these features that we're going to have to decide where the stopping point is. But I think that would be a good selection. We go further now. see over in this area, we're starting to select some of this colony as white. I think I want to back off this a little bit. Settle on about 163. Okay, so there's the beta in white now, and if we go and invert this image, so the beta is black, we can take our gamma, which is in black, and we can add the two together by saying keep darker pixels, which will take the darkest pixels from the current image and the darker pixels from the latest companion and fuse them together like that. Okay, so what that is telling us is that we've got gradient pixels probably around both the beta and the gamma that leave us with this strip separating them. Now, if we just inverted this and called it everything else, that's the kind of logic we want to do, because we don't want pixels double counted as both phases. So we've taken the gamma, we've added the beta, and we've inverted to say everything else is the colonies. But I don't think I want to call what's in between that colony. I want to call this either one phase or the other. So what I'm going to do is I'm going to dilate both by 1, both the gamma and the beta by 1, to say that we're not sure. We want to split this gradient down the middle here and say half of it goes to the gamma, half goes to the beta. So let's go up to where we've defined our gamma particles right here, and before this gets set as the companion and then added to the beta right here, I'm going to just add a dilation, EDM dilation, which, if you see here, grows black peak regions by a specified number of pixels in all directions, and that's what this depth value specifies, how many pixels in all directions. So we're just going to put a depth of 1 in there. That's going to grow that boundary by 1. And then it gets added and inverted. And now if we do the same for the beta, where is the beta defined? We go back down here, so right there, if we grow this beta also by 1, when we add the gamma to it and invert, now we are left with very few interface pixels that need to be sorted out, but they do need to be sorted out. We can't really just, although it's tempting to just erase small features and call this gamma, we then wouldn't have a fully continuous three-phase segmentation, because you'd have, if we erase these pixels, these pixels are black because they don't belong to either the beta or the gamma. So if we erased them out of the colonies now and didn't add them anywhere else, we'd be saying those pixels have no phase designation. They're effectively zero solutions. So your phase fractions wouldn't add up to 100 in this case. And it's not going to really, it's going to be negligible. I mean, your phase fractions probably will add up to 99.8%. But for the sake of thoroughness, what I would do is go ahead and put this state of the colony image in memory here. Hopefully this logic will make some sense at the end. And then we'll take all of these small black pixels here, and we're going to say keep everything that's under 20. So I'm just going to keep all of these little tiny pixels that are in question and assign them to the we'll have to choose a phase. Are they going to belong to beta or gamma? I'm going to say, why not gamma, since we already have that in our companion, in our companion slot. So if I go and now keep darker pixels, then I'm going to take all these small ones that used to belong to the colony, and I'm going to merge them in here now with the gamma phase. So the gamma used to look like this, and now it looks like this. It's picked up a few of those small pixels that we say shouldn't belong to the colony phase. Now I need to take back my think here. We want to go and take the small pixels that we've assigned to the gamma phase and subtract them out of the colony, so they're not in both. So we do have this point with our colonies where those little pixels are still in there as white. So we can go take these here and set them up here in a third memory slot. Okay, now they're stored away. We've added them here to the gamma. We're going to bring back restore image 2, which is the colonies with the small pixels in there. And we're going to set this up now as a different companion image, or as the new companion, so that we can then call our small pixels here and do keep darker. So now we've taken them out of the colony phase. So if we take a look at what we've got going on here, here's our colony. Let's call these colonies. And here's where we had the gamma have the little residual colony pixels get added to it. So this is my gamma phase. And then back here, when we dilated the beta by 1 and then added the gamma to it to start finding the colonies, this is going to be my beta phase. And now there are no double-assigned pixels. And we'll review the logic here to make sure that's the case. So, sequence. We flattened the background, put it away in memory, ran a first pass global threshold to get the gamma, got rid of small features, got rid of small white features, then decided we need to grow the gamma by 1 to get right at the get halfway into the gradient that is between it and the beta. And then we put this in our companion slot, and we went back to the starting point. Now we went after the beta, and we inverted it so that it's selected, and grew it also by 1, and then added the gamma to it, and put this away in a different slot so we could bring it back, inverted it to show the little dark features that remained in between where the beta and gamma got added together, kept those, saved them here, added them to the dark pixel, to the gamma, which is still in our companion slot, then took back the colonies before we dealt with those little white pixels, put this as the companion, brought back the little white pixels, erased them out of the colonies, or I'm sorry, erased them out of what will eventually be the colonies once we invert now. And then we assigned all our layers. So it can take a few minutes to build up all the logic, but now we've got a recipe that is pretty robust, and I would suspect would work very well for all other images like this. And if not, it would probably only take tinkering with each of these red steps to get it nailed. You want to look at the layers that we've made. There we go. So the colony is in red, the gamma is in green, and the beta is in blue. So there's a three-phase problem, which is the perfect time, I think, to move now to measuring phase fraction, which will just consist of us saying, I want to measure area fraction. Now, the first time you select it, it's measuring whatever you're looking at. So this one particular image is 67% black. If you wanted to measure each of these individually, go to your beta layer, run the area fraction measurement. There's 9% beta, go to your gamma, run it, 24%. Or you can generate report, which will make all of these measurements on all of the steps that you have set as layers. If there are no layers, all these measurements get done on the very last step of the recipe. So we'll generate the report, and now we'll get area fractions for our three layers. And 9 plus 24 with decimals looks like it adds up to 100.
You seem to be about good.
Good. So that's phase fraction. At the end here with the colonies, if we wanted to get some kind of colony size, we're going to have to do a few things. We're going to have to make sure that we're counting the right things. So obviously, if we look at the labels here, instead of using a single color, let's use a map. This is all seen as one big colony because they're connected to each other. So we can run a watershed off of the colonies to try to split these up. Just use a line thickness of 2 so I can see it. I like to start at 3. And if we accepted that, I think we've made too many splits. This shouldn't be split into 3. This should not be split into 2. Nor this. So let's edit the strain here. And try a weakness of 4, 5, 6. What's happening is that some of these small pieces are adding to the watershed's interpretation of where the things should be split. So what we could do is, for the purpose of size measurement, since you would probably count this colony as one whole thing, even though it's got some little bits of the other phase in it, is before we watershed up here, I'm just going to go get rid of some small white pixels, like anything as big as that. And get rid of anything under 450. just for the size measurement purpose. And now the watershed off of that, that's at least a little better. Let's try a weakness of 5 up here and get rid of that error. I don't know if that should be split or not. Maybe it should, maybe it shouldn't. Try 6, 7. So you do have, you know, a number of these little features that, for the, again, for the point of size, colony size measurement, I might want to ignore. So you could also ignore any black feature that's under 450 and call that now the colonies that you're going to measure for size. Now you might need to make a couple manual edits here. For instance, we might want to click on manual edit, which will add a manual edit step to the recipe. That certainly wouldn't apply to other images, but to quickly fix some errors here, we could say we don't want this to be split. So I'm going to freehand just fill that. Were there other separations that needed to be made or fixed? Maybe I'm not sure. We could play, maybe this should be separated here, so you could use a pen tool and make an erasure there. And now these are the colonies colored just on being separate things. Maybe this up here needs to get So this could now serve as an example of particle size measurement distribution. Imagine these are particles. They're a set of features in the image just like anything else. If we want to just get measurements and look at them as in a spreadsheet, then we can say measure features. I'm not sure what kind of metric we want to use for colony size. We could do colony area. We could do equivalent diameter, which is the size, the diameter that a circle of the same area as each of the colonies would have.
Yeah, major and minor axis too.
Major and minor axis.
Thanks.
We are going to add ferric diameter in here, which is the max chord length seen in the feature. Intercepts, I haven't used this in quite some time, but we can play with it now or later. So this will allow you to run 100 lines, let's say, through the centroid of every object and then report the mean length that passes through that feature with lines drawn through the centroid. So that could be a way of measuring average size. I won't run that right now, but we can run that later. And we're going to call this colony size. So those measurements were made now. So if we open up what we have, I've got a scale bar on this, so I should have elected to calibrate the magnification. Let me open up the original image. This is the same, even though it's a different image size, it's the same pixel density as the one I'm working with, so this micron bar is accurate. So start your distance line. Austin noted that this feature should be more obvious. There is, right now, holding down Shift does not snap the line to be straight. We're working on adding that feature. So for now, if you just right-click on the line and constrain the drag to horizontal, the line will only move horizontally. So let's set that to the micron bar, and say the length is 50 microns. So there's our micron to pixel factor. that you can save in a CalFactor library, let's say, for later loading. So I don't know what mag this was at, but you could say CalXY for a certain image dimension and a certain magnification. Then this would be valid for any other images taken at the same conditions. And all that is that number saved in a file. So if you cleared this out, then you could just load that in like that. And let's remake the equivalent diameter area, major and minor. Sorry, sometimes there's an issue if the file is still open in Excel, where we'll make sure that an error gets reported if the file has a save error. So the measurements are regenerated now in microns here. Now, if you want to visualize these measurements on something like a colorization on the features, we can do that in the color by measure tool. Even if you've never generated measurements, you can generate them right in here and they'll be read into a table automatically. Or since we've already made them, we can just pick the text file and have that table loaded in. I don't know if it'll make it in here by beta 7, but it's on our roadmap to add a histogram panel here on the right that lets you not only quickly view the histogram of any of these metrics, but also click on a bar, let's say, of the histogram and have only those features shown to you. That is something that we definitely want to get done soon. Right now, what you can do in this tool is take any of these columns and just choose any cell in that column, and now that column of measurements gets used to color the features. The row that you have picked is the highlighted feature. Click around and see what each of these features are. And now this tells you, this is the largest feature in the image, and what is it? And there's the ID tool here that goes the other direction, so pick that, click confirm, and it tells you what the number is and its different measurements here. So that's how you can make, say, particle size measurements and get the distribution and visualize those measurements. You can also look at, this is major axis length, minor axis length, area. You can hide the highlighted feature for saving purposes if you want. If you wanted to look at some other measurements, maybe you wanted to add eccentricity to this column. Oh, that file's open. Now eccentricity is also here. So yellower features in this case are more elongated. Bluer features are rounder. Now, just to see what it looks like, Austin mentioned being interested in measuring some kind of interlamellar spacing. So it's handy that we have all of the separated colonies here, because we're going to use this as a mask to only try to segment the lamellae within the black regions of this image. So to do that, I would put this in You see any, if I brought back, let's say restore 1, which is my filtered, well, not set, but call. If I look at my segmentation options here, anything with an asterisk in any of these menus means that it needs a companion image to operate. So the ones that are active and the key mutual features needs 2 binary images, a binary for the current and a binary for the companions. That's why that's grayed out, because we don't have a binary for the current. So the local threshold could be one that you could use to only try to threshold within the colonies, and that uses the companion to do that. So let me go and take my step here, which is where I have all of my colonies separated. And I call that my companion. But I think because the contrast here, this shows you all the separate features that are in that companion image. And you can choose to do an auto threshold on a per feature basis with, let's say, no deviation from the auto-determined value. And so it's now thresholding inside of each colony. But because the lamellae are so fine, I don't think this global type threshold within each colony is what we want to do. What I would rather do is use an adaptive threshold with the companion image as the mask, since now this will only consider and threshold pixels within the black features of the mask image. You probably want to go down to a very small window size. Wow, that's better than I expected. Creating this dark little outline here because I think the mask just starts to creep onto this gradient. So you might want to, before you set this as the restore, just erode this down a little bit so that you're not measuring lamellae at the edges of the colonies. So now this is, now what you want to do is have only the, because we could run now like a mean intercept type measurement on this result to try to get the mean distance across these lamellae. Depending on whether you wanted to measure the gamma or the alpha, if you want, so what's selected here? Gamma or alpha is lighter, I believe. So the alpha is the white in here, and the gamma is the dark. So if you wanted to measure the gamma, you're all set. You can just run random lines, mean intercept. And now the mean intercept through the black is 1.5 microns. If you wanted, now I wouldn't believe the mean intercept white because it's also counting these, spaces in between the colonies as part of its intercept length. That's why it's 3 times bigger. So you could, if we inverted this and then did a keep lighter, that would take the white from the companion. And erase it out of here. So now this is now the alpha. Let's look at the overlay. So there's the alpha lamellae, I believe. And mean intercept black on this image would give you the gamma, and mean intercept black on this image would give you the alpha. And I'm not sure if it's perfect or not, but I don't think that's too bad considering the magnification and resolution.
Better than I expected, John.
Yeah. Good. So we've got a big recipe here. Let's set up a couple of these as layers. We got the watershed here after the manual edit. Which you can choose to get rid of if you wanted a fully automated recipe. I'm going to call the I'm just going to add a random do a set restore 3 step here. I'm just going to call this the separated colonies so that if you did erase the 2 manual edit steps, then you wouldn't lose your layer set. So we're going to call these colonies separated. And then this is our not sure why the layers is not launching. Perhaps there's another issue that we've found.
Hey, John, this is being recorded, right, via video?
Correct. Yep.
Great. I'll be able to access that video later?
Yes, I will send everyone a link, hopefully by tomorrow, with recordings from today's and Tuesday's webinar.
Fantastic. Okay, thank you.
No problem.
It looks great.
Okay. So, whoops. Yeah, it seems like there's an issue adding a 6th layer. That's not been raised yet, so we'll add that to the list of things to get fixed by the full release. Sorry about that. So I'll send you this recipe file as well, Austin, so you can play with it. I guess there just won't be a lamella layer here, or we can get rid of the colony separated if we want to add the gamma.
That's fine. I think as far as the layers go, it probably doesn't need to be all together anyway. Just having that recipe there, I think, is useful enough when you're pulling data off. Yeah, it seems great to me.
Okay, so we spent a little bit of time on that problem. Hopefully that showed some tools and workflows that could be helpful in other folks' research. I've got, we've kind of hit the first 5 or 6 topics. We've looked at a thickness type measurement. Now, we can get into more of an in-depth discussion, I suppose, about precipitate thickness if there's anyone here that's interested. I know Austin is, and we've had some talks about that already, using what's called a Gunderson estimation off of your mean inverse intercept value, which applies a little equation to your inverse intercept value to estimate thin plate thickness as opposed to just using the mean intercept value. But that's probably better for more of an offline discussion, since I think that might be a little specific and may not be relevant to everyone else. But we've at least shown... Go ahead. Go ahead.
We'll talk about it later quickly. I have like 50 points, and I'm going to send you a presentation later.
Okay, sounds good. And anyone else that wants to get in on that, feel free to contact me by email. We can set up any kind of chat or personal screen share for that. Okay, so we've got pattern mapping next on the list, and then some more FFT filtering applications. But like I said, this might have been better suited to Tuesday. Is there anyone on that wants to see kind of a pattern mapping or FFT filtering discussed more in depth?
Please.
Okay. Which one is
mapping, so
pattern mapping? Okay.
If you had time.
Sure. So this image actually might be reasonably suited to show pattern mapping. You don't need it, I guess, in this case to separate features, since you do have stuff in between the colonies that helps. But let's say you only wanted to keep colonies in a certain layer of your segmentation whose features were going in a certain direction. You wanted to measure the amount of colonies that were oriented in one direction versus another for some kind of texture analysis. So we have our let's go back here. We have our colony separation. We have that as our latest companion, so that's fine. We can go down here at the end now. Let's just once again bring back our filtered grayscale image here. So in our feature finding menu, we have the pattern mapping available. And we can do a couple of things with this tool. So we've got 3 functions we can choose from. With 2-point correlation mode, you would give me one second here to just check on a couple of things. Two-point correlation allows you to calculate the what's called the 2-point correlation function around each pixel, which I don't have a visual to show you what it looks like, but for an area of very isotropic microstructure with no real directionality to it, it would have it's a 2D function, so it's going to have a hot spot in the center that's pretty round, pretty circular. For an anisotropic or directional microstructure, that window that you've measured, because you measure a window around each pixel, that window is going to have more of an eccentric hotspot. So we can map out different properties of the 2-point correlation function. We can map out the angle of that hotspot. We can map out its eccentricity. We can map out its size. We can map out its thickness. And that can help distinguish different traits of pattern from an image. In FFT mapping, we can choose to put a mask around, the same mask around every pixel's FFT and measure the amount of frequencies that fall into that mask on a per pixel basis. and map out pattern that way. And then with matching, we can choose a certain number of templates from the image. If we had, say, 3 different patterns in the image, this is usually helpful for high-res atomic scale images where you've got 3 structures defined by 3 different atomic arrangements in the image. You can pick a pixel from each of those 3 structures, and then every pixel in the image, its local FFT, gets compared to each of the 3 ones that you defined, and it gets colored based on which reference FFT it matched the best. And then these are tools for cleaning up the raw result from this mapping step to get to your ultimate segmentation. I will show the 2-point correlation here because that is, in my opinion, best suited for this type of image. So if we went with 2-point correlation, window size is going to be the size of the window that you use around each pixel. And again, you want to balance having a big enough window so that you get enough microstructural content per window, but not so big so that you lose spatial resolution, meaning that if you had a window this big, yeah, you've got great info when you're inside this one colony, but when you're at a boundary, you're going to have info from all kinds of different microstructural features. So you're not going to, it's like using a very broad electron beam to scan over your sample. You get tons of signal, but very poor spatial resolution. I'm going to go with 30, just because I think is a good place to start. The section grid is really just to get over memory limitations. This is a pretty memory-intensive process, so what happens is if you chose 5, you would split this image into 25 different segments. Within each segment, you get a 5x5 grid. That's what the number 5 means. Within each segment, everything is processed in parallel, but the sections are processed serially. I usually don't use any more than 3, and there really isn't any added overhead from doing. You probably could do it all in one image. You wouldn't have to split it up, but you get at least a progress bar that moves through the different sections if you use something more than 1. I'm just going to choose 3. The first time you run this, after 30 minutes of you last having run it, it's got to start a parallel pool that just aggregates your CPU resources and preps them for processing pixels in parallel. So that usually takes maybe 15 to 20 seconds to start, and then once it's been made, you don't have to make it for another half hour, maybe longer than 20 seconds. Sorry about that. I'm not sure what's going on. Start fresh here. Well, I can tell you this was working just fine yesterday, so I'm a little bit perplexed. Maybe we won't be looking at this today.
John, maybe we could do it some other time.
Yes. Well, you'll be, if you take a look at the recording from yesterday, then you'll see this work on there then. I'll try to figure out what exactly is going on right now. Try it one more time with a different window and see.
Hey John, sorry I wasn't, I was talking to somebody else, but sometimes when I'm using your software, some of these windows don't run through the calculation and I have to restart. Have you tried restarting?
Yes,
yeah, you did.
it looks
Okay.
like that's going now. Let me look into that, and all I changed here was the actual setting of the window size, so let me make sure that's not an issue. I guess if you run into that problem, just maybe set a window size of 30 physically instead of just clicking go. Go down to a 20 to speed this up. So if we overlay that on the original, we see some angles starting to emerge. It's a little bit messy, so why don't we let's go up to 40 and just let that finish. When you see this, this tells you maybe your window size wasn't quite big enough. You're not getting enough information per pixel. And there's also some the resolution on the lamellae is not always there across a colony. So there are going to be places where it has an issue resolving the direction. We can look at a different microstructure that might work a little bit better. So in this area, it's finding your angle pretty consistently around 40 degrees. Down here it has some issues, and around these features you've got some confusion in the local direction. If we went and now threshold on this angle map, and we only kept angles, okay, so first of all, we can also look at other traits. So we're displaying the angle property, but here's local eccentricity. So higher eccentricity values, again, are more directional. So in the deeper red areas, you've got more local more directionality to that microstructure, and in brighter areas you've got less directionality. So it can be used to segment colony from what we call basket weave type microstructures. I think I have an example of that. And then we've got radius, that is kind of a measure of local coarseness in microstructure. So you see your smaller values here, your bluer values are finer microstructure, and your darker reds are your coarser areas of microstructure. So some pretty helpful information that you can pull off just from a raw image with no processing beforehand. And the thickness feature is kind of the same information. I haven't made too much of use of this, but it can give you, I guess, a little bit different interpretation of coarseness and fineness. So if we wanted to just, let's say if we could possibly just keep the threshold on the eccentricity map, and if we just kept higher eccentricity values from 0.75 to 1, these are your areas of microstructure that are more directional. If we go back in here, we can switch to the radius and threshold on the radius. Maybe pick something down here. So these are going to be your finer, so-called finer areas of microstructure. And everything else is coarser. We went with angle, then we could, let's say, just threshold around the 40-degree mark. These are areas in your image where the features are oriented along this direction. May not be so helpful for this type of image. If you were trying to get, probably set our threshold a little more generously to keep all of this colony that was 40 degrees and then superimpose our colony segmentation that we had from earlier to just keep colonies that were 40 degrees. We've got another example image I can show that has all continuous pattern without any of these disruptions. This is an optical image that looks pretty scary initially. Let's just crop down to a little subregion here. Now we can go into our pattern mapping and let it run. The one we just looked at was thresholding on the raw data to separate out your features from your pattern map. Here we've got now the local directionality of all of these features here shown colorized, where you've got 50s and 60 degrees here, down closer to 10 and 0 degrees, and then up at minus 80 degrees. So we can run, we can bin these angles. We could say anything, consider 20-degree bins in your angle space to define your separate features. And now this lets you draw lines in between your separate features with a certain thickness. There are quite a few bins there. We can do some cleaning to get rid of these small features. Yeah, big coarse bins. We could get rid of anything under 50 pixels. And this would absorb these features into the the bin that surrounds them. Maybe not so well. We won't wait for that to finish again. I really have never had issue with that cleaning before, so I'll give that another try. But the water shedding is usually what I settle on when trying to separate out this continuum of angles. And we are going to fix this transparency issue right here. The watershed will go and it'll use a window to make a gradient, a window size to make a gradient map off of this to try to highlight the boundaries with strong misorientation across them. And then it'll run a water shedding algorithm on that gradient map to try to determine where to mark off the region boundaries from this image. So the default window is usually very close to the odd, or to the odd valued number that's closest to the mapping window size, but I will drop this down to something smaller. And now this is trying to make a feature map out of your angle map. You're now starting to define the regions of locally different pattern this way. Or you can do something like we saw last time with the last image, where you are, instead of, maybe you're after after quantifying the fraction of this image that is colony versus basket weave. So I would probably then switch to using eccentricity and threshold on that. Now these are your regions of more directional microstructure, and everything else is less directional, more basket weaved. So you'd want to have some calibration samples maybe where you said that I know there's 100% in this image and 0% in this image, and make sure that your pattern mapping parameters agree with that. And that would then help you define what the eccentricity threshold should be. So that's a little demo of pattern mapping there. Sorry about some of the hiccups, but it's important that we get these ironed out in the pre-release. So we're about a half hour left here, maybe a couple minutes further. If I look at my recording, you know, we're 2 hours and 17 minutes into the recording, so I want to save enough time for some 3D analysis for the folks that are interested in that. Is anyone interested in looking at some more applications of FFT filtering for getting rid of things like curtains in fib cross-sections or high-resolution image cleanup? Anyone want to see FFT filtering? Okay. Well, then we can move on to some 3D analysis, if that's good with everyone. Does anyone have any other questions related to any of the things we've covered in 2D so far? Feel free to stay on at the end too, if you want to talk about some more things in detail. Yeah, go ahead,
Yeah,
Austin.
sorry, I'll just save my question to the end. It's fine.
Okay, no worries. Okay, so thank you again to Abhishek for the images that you provided. Let me take a look at what you have here. Just got a few, but that's enough for a demo, I think. These are loading off of our data server, so they're not displaying too great right now. Let me go and show what a workflow would look like to try to fully reconstruct this little bit of microstructure. It all happens initially in the batch processor, and it's designed to let you do the entire workflow in one click so that you can take your raw data in, tilt correct it, follow an area of interest, align those areas, stack them, reconstruct them, apply your recipe. So you've got raw data in full segmented reconstruction coming out. But especially for this webinar, I think it's helpful to break up the workflow into a couple of pieces so that we can follow exactly what's happening to the data, and it gives you a little more flexibility and control over each step. So what I'm going to first do is, let me go into my file system here and see what we have. So we have the raw data. We're going to do a I think we'll probably do a pre-alignment on things, on the slices, then a final alignment, then a reconstruction. Let me set up those folders there. So we're not going to do any thresholding, so we're not going to use any recipe. We've got grayscale images. I'm going to put everything here into the realignment folder and add our raw images. Not obvious, but double clicking on these does open that particular image. We're not going to do any mag calibration because we are just stacking the images for alignment right now. We're not making the volume yet. I don't know if we'll need AOI tracking. I know we at least need correction because these are fib acquired unless they've already been tilt corrected, but I'm going to assume they haven't. And we're not going to do any alignment. We could do alignment during the batch processing, but I just want to see the raw data stack first. So let's just make a stack and process. So just make sure they're all the same size first, and then it'll just stack them up and give us a file that we can open. So let's go into the 3D toolbox now. On the left is where you look at image stacks, which are just sequences of images. On the right is where you deal with your reconstructed volumes, but we do have an alternative layout mode now. If you click this little button here, it hides all the image stack controls and rearranges everything just for reconstruction working, because typically you end up working with your image stack to get everything aligned and cropped, and then you make a reconstruction out of it, and you never use the left again. So we wouldn't want to waste that space for the user interface. But we need the stack controls for now, so let's open up here in the pre-alignment. We have the stack file that was made. And here we go, we can slide through the slices. So what I will probably want to do, we could do an alignment just on the entire data, but especially since there's a scale bar on each slice, and there's a lot of unmilled material around here, that's all going to dominate the alignment. So it's going to try to align all those features to each other since there's absolutely no change in them image to image. And we're probably then going to end up with, let's just see, let's try it. Edit align stack to first slice using translation. Oh, actually, you know what? Not much of anything happened because the micron bar was already perfectly aligned slice to slice. So if you view alignments, 0 happened. I should have thought of that. Let's undo that. And what I would probably do here is crop your area of interest down into this space where you obviously have some jittering of the microstructure, but that's okay. That's what we can fix. So let's do edit crop stack by drawing, and we'll double click on the box. And now that's what you get. So if we align on this data now, something better. So you can see, if we look at the uncropped, you get negative space in the areas that the images had to shift. And if you look at cropped, this is the mutually aligned space, where I think the alignment went pretty well. So sometimes you want to confine your area to something very small in the image to do the alignment, and then do export alignments to put them into a text file, reopen your original stack, and then do align stack by loading alignments and apply the alignments that were based off of a very small area, apply them to the full stack. But in this case, this is probably the area that we'd want to reconstruct anyway. So I'm just going to export now this stack into images so that we can make a recipe and reconstruct the volume. So I'm going to put these images right in the pre-aligned folder. And now we can, I think we already had kind of made a recipe. So let me just open up the first slice in our image processor Go back to the segmentation section here. Tell me I never saved that recipe from earlier. Looks like I did not. Well, we can make it quickly here. I think we had a median, we had a Wiener filter, we had an adaptive threshold of, pretty sure it was 30 and 101. And then we had a little bit of noise cleaning. And then some feature rejection. Now with the slices being part of a 3D data set, it's not so important that we nail the segmentation on a particular slice because we've got 3D information to work with. So we can do things like get rid of features that are only a couple of pixels thick that indicates they're artifacts. So we can probably just keep our recipe a little bit less severe in its noise cleanup and get rid of any artifacts in the 3D toolbox after we run the recipe. Let's get rid of some of these small black features. And we can even do the smoothing afterwards. Well, let's do the smoothing now. Let's do the 5 here. And then we rejected anything that got separated. So there's our segmentation recipe for the reconstructing. Let's go back into the batch processor now and load that. We're now going to save everything into the reconstructed. I don't think we didn't need a final align step. The initial alignment worked well. Let's go reconstruct and clear the images out and add our align set. No more tilt correction, no more image stack. I'm not sure what the scale of everything here, what the slice thickness was. Do you happen to know that, Abhishek? Do you know how much material was removed in each slice, or what the fib was set to? Is it maybe 100 nanometers?
John, it was 50 nanometers.
50? Okay, I thought it might be, just based on how thin the slice looked. We do have the XY calibration because you have your scale bar. Thank you. So let's set that. About 30 seconds to process these 15 images. So if you had 150 slices in your data set, then you're looking at 300 seconds, 5 minutes. And now back in the 3D toolbox, I can switch here to recon layout and open the reconstructions file. You do have all of your black and whites. They're not recon files, so you can't see them there. So all your black and whites are, if you have layer set, you'll have more than just one binary image for every slice. But we just had, we didn't have any layers, so the last step of the recipe got saved in addition to a reconstruction file that has your reference data and your segmentation and all the other slice thickness, pixel size, all in one file. And we've got all the same viewing modes here, so here's the black and white. Got those milling artifacts that are kind of running through the data set that are giving us a little bit of
John.
Yep.
Yeah, would it be nice to just crop the image a little more so that the jagged edge, which is milling artifact, can be removed out of the stack?
We could, but they kind of seem to move top to bottom. You want to just start right up here, just a little thin.
Yeah, that would be fine. That would be fine with me.
Okay. So yeah, we can do that. We can do that right here. We can edit crop reconstruction. Or not, huh? I know that was functioning fine in the last release, so we'll make sure that gets fixed before the full beta 7 comes out. Let's go back then over here to this side and crop the stack further. Let's reload this recipe on the first cropped image that we just made. Okay. And then let's switch out the aligned images for cropped images. Now you get a second reconstruction file that's recon01. Since we're saving all this to the same folder, it won't overwrite the last time you ran the batch processor. Everything will be in a processed 01 folder, and you'll have a recon01 file waiting for you. So let's open up this new one here. So here's our reference data. Now that might need to be realigned. The nice thing about having all this data together is that hopefully it functions okay. Whatever data you're looking at, if you're looking at the reference, you're using the reference. If you're looking at anything else, you're using the segmentation. We can go in looking at the reference and say, align the reconstruction to first slice. And it will align the data and then crop everything. So it aligned the grayscale, realigned it, calculated what those alignments are going to be, applied them to the grayscale, applied it to all the segmentations, and then cropped everything to the remaining volume. So now we just realign the data post-segmentation without having to redo the segmentation. So this first layer here is, the only layer is our alpha. We can rename that. Oops. Losing my mind. Call this alpha. We can duplicate this layer and call it beta. And then just invert segmentation. So now this is alpha, that's beta. The quickest way to get a 3D look at your microstructure is really just to first take a look at the reconstructed reference data here and say view volume. And you can slide through the slices here, either from the XY direction or from the YZ. There's a little sliver of microstructure. And whatever mode you're in here, black and white, you view that here in the 3D viewer. Here's the outline of your features. Mipar is not the greatest when it comes to the speed and power of 3D rendering. So we support not only export of your reconstruction, your actual voxelized volume, into either an Aviso or a VTK format. VTK is ParaView's open source, pretty powerful 3D visualization application. So you can export your data into that, either take the voxelized data, or if you make a surface, export your surface, if there was one, to VTK. If you happen to have ParaView installed, then we can make a volume rendering of our reference data by, if you have ParaView installed, this power render button will be active, and you can click that and it will export your data into VTK and then automatically launch ParaView for you and open up the data right in there. And then you of course need to get familiar here with this interface, but we really just use it for making some renderings of things. So we can our little sliver here. ParaView is available, I believe, at paraview.org. You can read in your you can take your segmentation here and export this into VTK. So this black and white. Open that up. We can take and draw a contour around the black and white. So if you have multiple layers and you want to visualize all of them together, this is a good open source platform for that. By supporting direct export into a VISO format, if you are fortunate to have a VISO, that's a fantastic visualization platform to bring all of your data together and make really sophisticated animations and movies. In Mipar, of course, you can make simpler animations and movies here. You can take your data here, whatever is shown, and if it's a volume like this, then you could rotate this, of course, about an axis. You can turn on your axes and labels as you'd like. Switch to pixels instead of microns if you want to. Change the background color. Rotate this around about an axis and make a movie, or make a clipping movie. Do the same thing with the reference data, make a movie of that. If you want to generate a surface of everything, that's all the features that are segmented, just click here, visualize all features, and that will calculate and render a surface around all features. There are your alpha laths. Seems like we got those lamellae pretty well segmented. If you had single features in here, which maybe you do, and take a look at your labels view, this shows you everything is colored now uniquely by being a separate feature. And this might have been one if not for this connection. So let me actually go in and see if I can separate out some of these features. So let's do a manual edit on the alpha. Let me zoom in here. I'm just going to take and draw a line. Make sure I split everything here. I can say apply this, apply it to all slices. That'll take that line and erase it out of all slices. I can do the same thing on the other side. Now that feature should be seen as a separate feature when we label everything. Everything gets relabeled, and yeah, they are now that. Those two are now seen as separate features, I guess. So if you've got individual ones that you want to just visualize, just take your other render tool here and double click on that feature, and then you'll get a quick rendering of just what that single 3D feature looks like. You can look at the microstructure, of course, from the other directions here in the 2D viewer. You can do your same rendering that way. You can get quick 3D measurements of individual features, so we just want to measure something about that, and we get that feature highlighted in that slice, and it tells us all these metrics about that one feature. Global measurements, total volume fraction alpha, 62%, volume fraction beta, hopefully 100 minus that. And take a look at a couple of these ribs. So these ribs were all interconnected, and then these were the two ribs that we separated. And hopefully by Beta 7 we'll have the other coloring modes supported. Right now these are auto-colored based on their labeling coloring, but we'll absolutely add the ability to color everything as one value. So we also want to support 3D coloring features based on any measurements that you assign to them, just like we can do in 2D. And then we can go a step further in 3D. Since we have surfaces, you can make surface measurements, thicknesses at each surface point, curvatures at each surface point. We'll let you use those values to locally color every point on the surface based on, say, its curvature. So a couple other nice things coming and a few things to get fixed before Beta 7.
John,
Anything we're hoping to see in 3D? Yes, go ahead.
so you actually segmented the alpha and the beta just prior to this 3D rendering. Can we just show both the phases in different colors in the 3D pane together?
Yeah, that's not at the moment. That's another thing that we'd like to support as soon as possible. No, there's no show them in different colors.
Okay.
The easiest way to do that would,
You go to ParaView, right?
yeah, there's absolutely a way to do that in ParaView. If you read in the alpha and the beta as VTKs, play with the visualizing in here, and you should be able to do that, no problem. But yeah, right now it's one layer visualizing at a time here in Mipar. But we'll try to get a layers view added here. That would be helpful. It just could be confusing because it wouldn't be. No, that would be a helpful, absolutely be a helpful feature. You just have to keep track.
Because I would like to, I would like to see how the alpha and beta phases are intertwined, together.
Okay, I see. Well, if you so if you have, I mean, you can see that now. You just you're just, instead of it being two colors, it's white and black. On the 3D side, if you had both phases with surfaces drawn around them, it's just going to look like a multicolored block.
Right.
You're probably going to have to, render surfaces in ParaView, and you should be able to clip away one surface while you keep the other one intact, and that might help you get a better view of how they're intertwined.
Right.
You could also make, you could make surface area per volume measurements in Mipar, and perhaps if you compared that measurement across different microstructures, that could correlate with the interpenetration.
Right.
I'd be happy to show you how to do all of that visualizing and clipping in a Viso, but I don't know that you have access to that. I'm not as familiar with ParaView's visualizing tools.
Oh, well, I have access to Amira, so I have already tried that kind of a thing in Amira.
Okay. Well, yeah, I mean, we have, so your alpha is right here. What I would do is I would say export this reconstruction with alpha shown to a Viso. Kind of the convention is here. Almost any of these tools will take, if the reference is shown, then they're operating on the reference. Like the export tool, export to a Viso and BTK, you're using whatever is shown. Filtering will work all off of the reference data, segmentation off of the reference data, and then cleanup off of the segmentation, whatever layer is shown. So if I wanted to just export the segmentation to a Viso, then you'd want to use the black and white view. If you wanted to export the label, you can also do that, and that'll export all the labels into an Viso format, so you can differentiate without having to run any Amira sort of labeling functions. You would have all the separate features in an Viso file if you were in labels when you did export. Let's just quickly do the black and white here for alpha. Let's export alpha to a VISO. I will have inside of, let's just make an VISO folder here. We'll dump that in here. And then let's switch to beta. Also do that little pause that's happening every time you switch. It's relabeling the reconstruction. So if you have a really big data set, that can take some time. If you just want to switch layers for whatever reason without wanting to wait for that, then you can uncheck this auto relabel, and it will avoid that. It will just inform you that this number of features in your data set may not be accurate because you haven't relabeled the features since you switched layers or made any modifications to the segmentation. Just a note there. So we did the alpha, there's the beta. You're just picking a folder to put it in, and it puts what the VISO file format is kind of best kept as. We could export as AM files, which is a native Amira format. That's not the one that we export in right now. It's this text file is really the file format, and that then reads in all of the slices with all of the. I'll show you what that text file actually looks like here in WordPad. So that's an Amira stack slices format, and it's got the pixel size and all of the files to read in with all their Z positions. So all you need to do is drag the text file into a VISO or choose to open it in a VISO. That will get all your data read in. Let me just open up the right version here. While we're waiting for that to launch, there we go. So let me take my here's the alpha. We might as well go grab the reference data. I think my screen sharing might be disabling the volume rendering ability. Yeah, so I won't be able to show that, unfortunately, but so we can look at what you wanted to see was, let's turn that off. We'll go just threshold on the, because in order to make a surface in the VISO, you need to have a label field defined, which you can do in a couple of ways, but it's probably easiest to do interactive threshold. We're just going to threshold on the zeros of each of these data sets. So those are the black pixels for alpha. So there's the zeros of alpha, apply, and now you've got something you can make a surface off of. And let's hide the threshold. Make the surface with constrained smoothing. And now view the surface here. There's the alpha surface, and the beta. Those are your two surfaces right on top of each other.
Yeah, precisely what I was talking about.
Yeah. But you're still going to have to look at one kind of without the other to judge any sort of
Obviously.
right? You could take surface cross-section through the alpha and clip that and show the beta. So once you've got your segmentation and alignment and everything in Mipar, you can do some visualizing quickly in Mipar, but to really play around and do a lot of this visualizing playground type of stuff and movie making. If you happen to have access to a Mira or a Viso, that's fantastic. ParaView is a pretty good open source solution, and we are actually in an agreement with FEI, who is now the owner of, or I guess the owner of Viso and Amira, to start integrating some of Mipar's features into their products to help integrate Mipar's segmentation and other tools with their visualization environment. So that's an ongoing project, and we'll keep you posted.
Oh, that's wonderful.
So that was a quick show on 3D. Anyone have any questions on the 3D part or comments or anything? Any questions in general? Besides Austin, I guess?
Hi, John.
Hi, Biswajan. How are you?
Yeah, I'm fine. Is it necessary to have some markers in order to stack any particular set of images?
It is not necessary. As you saw with this data, we use the microstructure to align itself. If your microstructure is random enough, then it can be used for that purpose. If you had, let's say, an alpha colony that you were trying to align, and you only use the microstructure for its own alignment, you're going to end up coming out with nice, perfect, straight alpha laps up and down, which may not be the case. If they're inclined, they'll get artificially straightened by the alignment. So in that case, we like to, if you have fiducials in place, then if you run into that case, I think it's probably easiest to set up a webinar or a screen share between us, and I can show you some ways that you can pre-filter your images and do it on the filtered versions that try to just accentuate any fiducial markers, and then take those calculated alignments from the filtered images and apply them to the raw images so that you're really using fiducials or markers to do the alignment.
Right. Okay.
So let's take a look at any of those cases when you run into them.
Yeah.
I took a quick look at your data set, and we'll need to look at it a little bit further. There seemed to be a lot of material that was removed from slice to slice.
Exactly. Yeah.
So yeah, I need to look at that further. We might have to do a lot of resampling and interpolating to get any kind of
Yeah.
reconstruction through there.
because all the sections were done manually by manual polishing. So
Right. Yeah, if there's a dramatic change in microstructure from slice to slice, then
hmm
the best kind of reconstruction you're going to do is just an approximation. You're just kind of guessing
okay,
at what's happening in between slices.
right. Okay.
But let me take a look at that a little bit more carefully and see the best that we can do.
Okay. Okay, John. Yeah.
Okay, good. So we're 2 minutes past the 3-hour recording mark, so pretty well on schedule. Hopefully everyone found some relevance in the different topics. This is all recorded. I will go through this recording and Tuesdays and try to timestamp everything so that there are chapters through the different recordings so you don't have to watch the whole 3 hours to find what's helpful to you. I'm always here for more custom tutorials. We're going to try to get more tutorials up on the site. We're working on a manual. We've got plenty of bugs to fix before Beta 7 that hopefully will be out next week or the week after. Hit me up for any recipes that you need. Anybody have any last minute things? Besides, I know Austin for one.
Yeah, John, I was just probably I missed this information from the website. But what is the recommended hardware for the PC in which one should run Mipar?
Sure. But of course depends on what you're using it for. You do have up on the About page some recommended minimal specifications.
This is way down there. That's why I missed it.
Um, if you're just using it for 2D analysis, then a quad-core workstation with a decent discrete graphics card and either a 7200 RPM or SSD hard drive or fast network storage and at least 8 gigs of RAM. Even 4 gigs you might be able to get by with depending on your image size. For 3D type work, yeah, you're going to need more cores, a bigger graphics card, as much RAM as you can get, fast hard drive for data loading and writing.
So my PC just meets the minimum system requirements. So I suppose that is why it every time shuts down whenever I'm trying to segment my image.
That I don't think so. I got your email about that. You said you were still running beta 6. You could try this pre-release and see if that still happens. I know you said
I tried with the I tried with the pre-release, the latest one which you sent across, and it again shut down even with that.
you, and you said that was during when you tried to run the feature smoothing and the manual editing.
Yeah, yeah,
Okay.
or the outlay.
Okay. Um, let's set up another support call or email for that, and I'll need to know what the exact specs of your system are, and we'll run Mipar in debug mode and see if there are any errors that are output that indicate the problem of the crash. It sounds like a graphics issue. Do you know what graphics you have? Do you have an integrated Intel chip, or do you have an NVIDIA card in there?
It's the Intel chip.
Intel chip, okay. Yeah, that's an unusual one. I've encountered that. I think just once I remember someone having that issue.
Okay, so my graphics card is Intel HD 3000 series.
Intel 3000 series, okay.
Yeah, and whereas it says 4000 as the minimum system requirement,
Yeah.
and I'm running a Core i3.
Okay. Yeah, well, let's see if we can troubleshoot that further and see what the cause of the crash is. I'll send you an email telling you how to run Mipar in debug mode, and we'll see if we can figure it out.
Sure.
The only system you have access to?
No, I have a higher RAM system, so I can try running Mipar there as well.
Okay, yeah, give that a try and see if you have the same issue.
Sure, sure,
Get it fixed on that one.
sure.
Okay, very good. So I guess Austin has very patiently hung around for a couple extra questions. Everyone's welcome to stay on for that discussion if you'd like. Or I know it's probably pretty late for a bunch of you, so
Yeah.
if you take off, thanks very much for attending, and stay in contact.
Yeah, sure. Thank you, John, so much.
Yeah, no problem, guys. Thanks so much for your 3 hours of time.
Thanks and good night, John.
All right, take care.
Yep. Bye.
Good night.
Fine. John. Bye.
Take care, Jiashen.
Yeah, John. So I think I don't have that many questions, but I probably will need you to direct me to some places where I could learn more, either videos. I was a little busy when you were asking about it, but I did want to learn about the high-pass filter.
Yeah.
But I probably, typically these images are pretty pristine, or at least if they're not pristine, we could just get someone to measure it again. I mean, they're usually just SEM or just some optical picture. So it's not so bad. I think what I'll be asking you about today is the thresholding.
Okay.
So the process you set up was good for the optical micrograph I sent you. And I think that the procedure that I went through, and then you helped me refine a little bit, worked out really great. Especially with the intercepts, I think that it matched up really fantastic to manual measurements.
Good.
Which, I'm doing more and more to make sure it's not just coincidence. But I think that so far, when looking at big rectangles or things that approximate them, it seems like the intercept method is pretty good. Or it's good enough, anyway.
Yeah, okay.
I think you're... Oh, sorry, go on.
No, those are great case studies.
Yeah.
That's all about.
Luckily, there's some other interns who are sometimes free, so I can grab their help.
Yeah.
Yeah, so the optical micrograph, I think it was okay. I think today I'm going to ask you about thresholding. I have a backscatter image
Okay.
where instead of the alpha being light, the alpha is now dark, and the beta is light.
Right.
No. So
Sure.
things changed a little bit.
Let me, we go to Tuesday's session.
Yeah, if you want, I could send you an image. Or would you prefer just to look on my screen?
Yeah, go ahead and send me the image if you could.
Sure. I think these are TNM titanium images. Okay. Yeah, that was great. Tom was impressed. And I think that's it. And I'm hoping we'll go forward and purchase this. But before I do, because I'm just an intern, and once I'm gone, the expertise is gone. So I need to write down procedures for them. So I just want to make sure I cover the majority of cases that they'll be working with.
Sure.
Yeah. But anyway, it's still like I just don't think you could do this on ImageJ. It would the amount of training it would take would be it's rate limiting. You can't. I don't think it's. I don't think you could do it in industry.
Yeah. Well, that's great to hear. We like to be, we like to be way better than something like ImageJ, especially when that's free, right? We better be.
Yeah, I understand there are other softwares available too. There's something called Forva or some other thing like that.
No, there are a number of commercial packages, but this is probably one of the few that's designed by actual material scientists.
Yeah. Yeah, I noticed. Anyway, I think that I mean, I personally am sold on the amount of analysis you can do.
Mm-hmm.
All right, so I'm sending you a picture. Okay. Yeah. Okay. So now this is a little bit different. For one thing, it's a lot cleaner, but the brightness varies a little bit
Oh yeah.
between the lots.
Where'd you get
Let me know when you...
Where'd you get these pictures?
Okay, so this comes from a paper on that's the titanium aluminide alloy TNM.
Okay.
I believe it's yeah. I think it's the same reference I sent you.
Okay. Very cool. I just
Yeah.
asked I couldn't tell. The one on the right especially, I felt looked like one that we had published a while ago from a paper on titanium microstructure quantification of Ti-6-4.
You know what? It may just be from you. I don't know.
That's totally nice looking micrographs, so sure.
Yeah. Well, you
Very
should be
cool.
proud if it's part of your group.
Well, I think it was taken before I joined the group, but yeah, it is.
That's yeah.
Okay, good. So let me go and take this here and
Yeah, it's quite possible that I took this picture from the Gundersen analysis.
what did I sent you? Yeah.
Yeah.
Cool.
Right.
One moment here.
But so I had an intern help me out, and well, of course I'm an intern. I had another intern help me out and do about 1,200 measurements on that picture.
Wow.
Yeah.
The A.
Sorry, what?
The A image.
Oh, yeah, the A image, exactly, not the B.
Okay.
Hold on, let me just, here, that should, can you hear me?
Yes.
John?
Can you still hear me?
Yeah, is this better?
Before it was fine, but yeah, you sound good.
Okay, great. So, he took 1,200 on the A.
Okay.
And so this is another test case. I guess I saw it in the Gundersen paper and thought, hey, that's a really nice, clean-looking micrograph.
Yeah.
Yeah.
Good.
Okay, so I was, so when you do this, just some sort of automated thresholds, it cuts off just a tiny bit. So if you were just to load the recipe, which of course is no longer valid here, but what would be the steps involved for this one? And during that, I want to ask you about local thresholding.
Okay.
Because I noticed in some places it will overcorrect, in some places it undercorrects. And I was just wondering if local thresholding could help there. But I think that I would learn a lot if you just step through this picture real quick.
No problem. Let me save this one here. Save as.
Yeah, the videos are great. I might even take the video you send me and like cut it down, just for presentation purposes.
Okay.
Do like a few quick ones.
Just right. The one that we'll go through right now, you mean?
No, not this one.
Okay. The one that I sent you previously.
Yeah.
Okay. I'll tell you what, let me go ahead and we'll go ahead and end the Mipar webinar recording right now, and the rest of this will be a video that we'll save just for you if you end up needing it.
Oh yeah, that'd be great. Thank you.